Well, hello everyone. My name is Burak Uzkent from Rochester Institute of Technology. Today I will be presenting our work on high-speed object tracking using multiple correlation filters. This is a joint work between myself and YoungWoo CEO, who is an engineering team lead in Hyperloop 1. So the motivation of our work is it is very desirable to have small footprint and highly efficient tracking algorithm running at real time on low-cost embedded system. And on such platforms, we won't have GPUs, and we will have computational limited CPUs. And then achieving a real-time operation on such platform is going to be very tricky. And then, unfortunately, the most recent trackers are tested on computationally powerful machines, including i5 and i7 processors. And for the deep learning case, they are tested on expensive GPUs. And then, however, we won't have those luxuries on low-cost embedded systems. And then here we actually perform some experiments to determine how well we need to perform on powerful machines, including i5 and i7 processor, so that once we translate our tracking algorithm, it will operate at real time on a low-cost embedded system. And we determined that it should be at least 300 frames per second operation rate running on i5 or i7 processor. So there are a number of traditional computer vision algorithms that can achieve that. They all rely on the correlation filter idea, but however, they have major drawbacks. So in this study, we will try to address those drawbacks. And then what does kernelized correlation filter tracking does actually? It poses the tracking problem as a rich regression cost function and try to minimize it in the frequency domain. And because in the frequency domain, then we can just do element-wise operations rather than convolutions. And then we can also make use of circulant matrix because it can be diagonalized by discrete Fourier transform. And then we can arrive to this nice, efficient primal domain solution. And then we can also transform it to dual domain to get more discriminative tracker. And then this can run at larger than 300 frames per second. However, it is not scale adaptive. So in this study, we will try to address the scale adaptiveness issue of EnKCF, kernelized correlation filter. Yep. So we basically utilize a number of correlation filters in a coherent framework to perform adaptive scale tracking while achieving a larger than 300 frames per second operation rate. And in the first frame, we initialize 3 correlation filters focusing on different areas. And then we also initialize a simple particle filter. And in the next frame, we run a large area translation filter together with particle filter to estimate translation. And in the following 2 frames, we operate smaller area translation filter as well as particle filter as before. And finally, in the 5th frame, we update our scale using the scale filter, and we only rely on particle filter to estimate the translation of the target. And since we do not use any translation filter in this frame, there might be some drifts, and we try to address those drifts in the next 2 frames using large area translation filter. So we basically repeat this pattern in the following frames and try to achieve scale adaptive tracking. And then the idea is, so we have 2 different modules, particle filter and EnKCF with multiple correlation filters. And then basically each correlation filter try to address the problem of the other correlation filter. And then this is the way we represent the objects in different correlation filters, because we will have this freedom in each correlation filter. So in the first one, since we focus on larger area, we concatenate Hawk features with color naming features. In the second one, we only use Hawk features. And for the scale filter, we focus on the target only area, and then we concatenate color and Hawk features, because scale update is very important. And then we perform some experiments on the UAV123 dataset. And then we first compare it to high-speed trackers, and our tracker outperforms them by at least 15 to 20%. Meanwhile, we also compare it to low-speed trackers. However, they are computationally very intensive, and they require powerful hardware to run at real time. And then we also perform some experiments on the 10 frame per second version of the UAV123 dataset. And as you can see, all these state-of-the-art trackers, their performance go down dramatically, which is a sign that our tracker will outperform them on low-cost embedded system. And then finally, we actually try to understand the optimal order of deployment of different correlation filters. And then based on like, these are all different sequences we follow, and then we get the best results with the EnKCF framework, considering the trade-off between speed and accuracy. And then you can find our C++ code in our GitHub repo. Please let me know if you have any questions about our tracker, and then I will be happy to meet you in our poster session. Thank you.